All right, in this video, I wanted to give you an example of how we can use the rules for adding capacitors, whether they be in series or in parallel, to basically take a rather complex arrangement of capacitors, break it down to the point where it's just one capacitor, and then how we can use our information to go back up in order of, complexity and figure out, as we trace our way back, what the voltage and charge would be on each of the capacitors. So we finally get back to the original situation, but now at this point we know for each one its voltage and its charge. So just to remind you, when we think about capacitors being connected in different ways, we really divide it into series and parallel. I find the easiest way to think about it is to follow the wires that you see in the diagram. So if I am going along in this branch right here of this circuit, I follow the wire to one capacitor, the wire comes out the other end and it goes directly into the next one. That's a typical example of two capacitors that are in series. Now we also see in this diagram that we also have some examples of capacitors in parallel. Now the way that we can determine when there's capacitors in parallel is we reach a point in the circuit where the wires branch into different directions. And each of those branches then are in parallel with each other. So right here we see there's a chance for the wire, it goes in three different directions. It goes over to this side, and down through the middle. Notice at the bottom, the wires come back down together again and join. And so between those 2 points, we have three branches that are in parallel with each other. So this is in parallel with this, which is in parallel with this. Added bonus over here, we have the example of these two that are in parallel with each other, but which are also in series with the 1.5 microfarad capacitor. So there's a lot going on here, but I wanted to do something that was pretty complex on a video because you could have the chance to sort of watch and stop and see all the steps that are involved in doing this solution. Now when you're tackling a situation like this, you kind of go from the most complex to the simplest thing. Now, for instance, I know I have three branches in parallel, but I would like to get those down to a situation where there's only one capacitor in each branch. Over here, this branch is the one that's the most complicated because these two are in parallel and they're in series with this one. So I'm going to start with these two capacitors. And what I want to do is I want to use the rules of capacitors in parallel and replace these two capacitors by a single one that has the equivalent value. Now, there's a 15 microfarad capacitor and a 3/4 microfarad capacitor. If I look at the rules of parallel, to find the equivalent capacitance, I simply just add these. And so the equivalent capacitance to these two in parallel is one capacitor that has a capacitance of 15.75 microfarads. So I'm going to redraw the diagram. And so, I've been doing this for a long time, but I still like to redraw the diagram. So don't be shy about doing that because it's a lot easier to keep track of what you've done. So I've replaced those two that are in parallel with each other by the 15.75 microfarads. And now I have two places where I have two capacitors that are in series with each other. And so I'm going to add those together in the proper way using this rule and use that to be able to replace those capacitors with a single capacitor. So 1 over the equivalent here is equal to 1 over 1.5 plus 1 over 15.75. If I add those two together, I get 0.73, which is 1 over the equivalent. So the equivalent to those two is going to be the inverse of this value, which turns out to be 1.37 microfarads. Notice I don't have to carry along my the microfarads. I can just use the whole numbers. I'm going to do the same thing for these two over here because they're in series as well. So 1 over that equivalent is 1 over 5 plus 1 over 3.5, which gives me 0.4857, which means the equivalent of those two added together is 2.06. Now, I've made this drawing a lot simpler. I'm going to just put the picture over here so I have some breathing room. So now I have 3 capacitors that are in parallel with each other. The one over here I found to be 1.37 microfarads. The 8 microfarad has just been coming along for the ride the whole time. And this one over here I found was 2.06 microfarads. When I add those 3 together, those are 3 that are in parallel, so I can simply add those together. And when I do that, I get 11.4. So basically, this whole thing, this ended up to be equivalent to 1 capacitor with the capacitance of 11.4 microfarads. So I went all the way from having 6 capacitors to 1. And it only really took me a couple steps, not too bad. But the thing that's really, I think, most challenging is when we try to work our way backwards. And we want to be able to figure out, given this equivalent capacitance, if I tell you what the voltage is across this capacitor, which would have been the potential difference from here to here to begin with, then we could actually figure out the charge and voltage on each of these individual capacitors. To do that, we're going to use these rules about charge and voltage. And we're going to work our way backwards from where we got to. So for this example, I just said that the equivalent voltage across the whole arrangement of capacitors was 5 volts. And I probably should also write up here for reference, the definition of capacitance is charge over voltage. Because as I go through this, there's going to be times when I have to rearrange that expression to be able to calculate maybe either the charge or the voltage on a particular capacitor. For instance, here I have an equivalent capacitance of 11.4 microfarads. It has a potential difference of 5 volts, and I might say, okay, so what's the charge that is on that capacitor? That's going to be equal to C times V, which is going to end up to be 57.2 microcoulombs. Now that's the total charge on this equivalent capacitor. Now to work my way backwards, I'm going to always have to say, think about how did I get from here to here, but now I'm going backwards. When I got to this equivalent capacitance, I realized I was replacing 3 capacitors in parallel. Now, one of the helpful things that I know about capacitors in parallel is they all have the same potential difference. And so the potential difference across this capacitor, which is 5 volts, is the same as the potential difference across each one of these capacitors. So I'm going to write in here that each one of these has a potential difference of 5 volts. I did that because that was the easiest thing for me to sort of go from here to here was just what value would be constant. Once I know the capacitance and the voltage, I can actually figure out the charge, because again, the charge would be the capacitance times the voltage. And so using that fact, I have, this would be 10.3 microcoulombs. This would be 40 microcoulombs. And then this would be 6.85 microcoulombs. And this is actually right, not 10.3. It would be 10.12. Sorry about, oh, it looks terrible. You can't read it. Let me erase that better. Oh, yeah, it is 10.3. What am I doing? Now, how could I test myself? Now, as I go through this, there is going to be a little bit of rounding, but think about what also is true about capacitors in parallel. What happens is the charge splits itself up among the capacitors that are connected in parallel in such a way as to keep the voltage across each one of them the same. That kind of means that there's no preferred path then. It doesn't really matter if I go through this, the middle or the sides. It's all going to be the same cost in terms of energy because of the same potential. But because of that rule, it turns out that the total charge that was available to be distributed among the capacitors is simply the sum that you find on each of the capacitors. What I'm getting at is we could kind of test ourselves by adding these three charges and see that they're approximately the same as 57.2 because that was the total charge that we had available. With these problems and these crazy numbers that we have for capacitors, there might be a little bit of rounding. So if it's not exactly the same, that's okay, but it should pretty much be the value here. All right, so you saw us do one step. Now let's go back to this arrangement. Now, in this arrangement here, we had two capacitors that were in series. The 1.37 capacitor is taking the place of these two, and the 2.06 capacitor was taking the place of these two. When we look at for the rules of capacitors in series, what we find is that when they're in series, they all have the same charge. So the charge on each of these replacement capacitors is the same as the charge that's on each one of these. So for instance, on the 1.37 microfarad capacitor, we have 6.85 microcoulombs. And so that is the charge on both of these capacitors. We know that they have that charge. Likewise, this 2.06 microfarad capacitor stood in place of these two that are in series. The charge it has is 10.3, which is going to be the charge that's on each one of these. Now, for those two capacitors, I know what their capacitance is and I know what their charge is. And so by rearranging this expression, I can find the expression for the voltage across each one of those. And the voltage will be found by taking Q over C. And that's just, we're rearranging. And if I do that, I get that this has a voltage of 2.06 volts. This one has a voltage of 2.94 volts. And this one has a voltage of 0.435 volts, pretty small. And this one has a voltage of 4.57. Didn't really do anything with the 8 because everything about that remained the same. It had a charge of 40 microcoulombs and a potential difference of 5 volts. And again, now what can we do to check our work? The voltage across two capacitors in series adds up to give the total potential. And what we found was that these replacement capacitors had a potential difference of 5 volts. which means the potential across these two added together should add up to be 5. And you can see that it's 5 when you add the 4.57 and the 0.43, the 2.94 and the 2.06. Those are going to add together to be 5. So now we have almost everything figured out because we figured out the charge potential of these two, the one in the middle, and the 1.5, and now all we have to do is think about this capacitor, which was standing in place of the two in parallel. Now, what did we learn about capacitors in parallel? We learned that they had the same potential difference. So these both have a potential difference of 0.435, and then I can use that to figure out the charge on each of those. So I get, this one ends up to be 6.52 microcoulombs. And then this one over here is actually really small. It's like 0.32 microcoulombs. Again, those two should more or less add together to add up to be 6.85 because this capacitor stood in place of the two in parallel. It had a charge of 6.85, so these two added together should be 6.85, and they both have the same potential. So I know it's a lot, but all the steps are here, and because you have the video, you can stop it and look at it as much as you want. But again, the idea is to sort of start with the most complex part of the circuit and gradually replace each of those complex pieces by a single capacitor until you get to the stage where you have one capacitor. Then if you know the potential difference across it, you can find the charge, and then you start working your way back through your pictures. And this is why I like the pictures, because I don't have to like try to do the work in my head. And using the rules for charge and voltage on capacitors in series and parallel, you can decide how the voltage and charge goes through these stages.